Hello, I am David Zhang, and my teammates are Michelle Lee and Nikhil Nayyar. Our project focuses on the development of a testing system to support the research of encryption algorithms capable of defending against quantum crypto attackers. The Quantum Permutation Pad, QPP for short, is a simple encryption algorithm that does not require the use of quantum computing and yet provides adequate protection against quantum computing attackers. Expectations of the project include being able to simulate an end-to-end encryption system, possibly with attackers, on a single system-on-a-chip platform to evaluate the QPP algorithm against AES. The system-on-a-chip chosen is the Zyble Z7 board. The prototype features a functional implementation of the QPP algorithm implemented using C++ and translated to register transfer level code using Vitis HLS. However, the prototype still requires the integration of certain components such as the Python graphic user interface and the synthesized hardware logic block of the QPP. Our project sponsor is Dr. Stephen Knudsen from the University of Alberta. The C++ implementation of the quantum permutation pad algorithm was successfully implemented. The user can specify the different number of permutation gates used in the encryption process, as well as the respective sizes of those permutation gates. Now, we realized that certain functionalities like a pseudo-random number generator couldn't be used in the C++ implementation of this algorithm because we also needed to synthesize the code into the register transfer level. And so this functionality will be incorporated into our Python graphic user interface and administrative software in the future prototypes. In QPP, the message sender and receiver use an identical key to encrypt and decrypt data. Using the shared key, QPP encryption generates a selection of fixed-sized square matrices. In this following example, we have matrices of size 8 by 8, and these matrices are known as permutation gates. These gates are used to encrypt each chunk of the input message. The matrices are also binary, and as can be seen, only contain one 1 in each row and column. So this recording demonstrates the point of view of the user after further development beyond the current stage to integrate the QPP logic block with the Python graphic user interface. These are the permutation matrices generated by the algorithm. In the full implementation, instead of having 10 of these matrices, there will be 64 of them. But for the sake of demonstration, we only printed 10 here. Now I'm going to enter a test vector, for example, hello world. Hello world. And as we can see, the input length is 13. We have the original message, the ciphertext that is produced by the encryption. This cannot be represented in ASCII, so we see a bunch of question marks. And the decrypted message at the receiver side is the original message. Now, what we see in the following rows here are the bits of each ASCII character from the original input text. And so this is the original bit representation of hello world, whereas here we have the encrypted version. So it's scrambled and cannot be translated back into ASCII. So it's encrypted.
We were able to run a custom Linux image on the Zyble Z7 board using the PyLinux tool. The Linux image contains packages for Python, allowing us to run the software components for the testbed. These include the graphical user interface and the command line interface. The Linux image also allows us to write to the DRAM on the Zyble Z7 board to facilitate communication with the FPGA portion of the board, where the QPP algorithm is implemented. Also, our image allows us to include the FPGA bitstream of our QPP implementation. This allows the board to be programmed with QPP upon boot up. The image on the top left shows the microSD card we used, which contained our Linux image, as well as how it connects into the Zyble Z7 board. Below is another image showing Linux running off of the board. Another part of the project that worked was creating the GUI and the CLI. These both provide the same functionality of various configuration parameters for the testbed. These include choosing an encryption mode or an attack mode to simulate cryptographic attacks. You can also choose the encryption algorithm to be used. Both of these software components also perform the ability to automatically generate test vectors to serve as the input data to the QPP algorithm. The number of these test vectors as well as their length can both be configured. The GUI and the CLI were both programmed using Python, and they are included within the file system of our custom Linux image. In the image of the GUI, you can see the parameters that can be configured as well as the results displayed. For the QPP testbed, we were not able to display the GUI from the Zybo to an external display. This was due to various drivers needed in the Linux image, as well as hardware blocks needed in the block design in Vivado that we were unable to develop. In the image on the left, we were able to display output from the Zybo using a pre-built Linux image. However, we were not able to replicate this feature using our own custom images. Another part of the project that did not work was the communication between the processor and the FPGA of the Zybo Z7 board. Our plan was to use the DDR memory located on board, and in the image on the right, we were able to read and write to the memory from the processor. The next step would have been to read and write to these same addresses in our QPP algorithm, which was running on the FPGA, but we were unable to do so.
Currently, Linux is installed on this microSD card. So this is our Linux image that contains the command line interface. And to boot up the system, we just need to insert it into the Zybo board, switch on the Zybo board. And as we can see, it's connected to this laptop here. So right now, Linux is booting up. So once the Linux system is booted up, we can run the CLI. We are logging in, and on the screen we can choose the mode. So we can either encrypt some text or initiate an attack simulation. Okay, so we're choosing to encrypt, and we can input the length of the test vector, number of vectors generated by the system, and as we can see, some test vectors are generated. So now we can choose the encryption algorithm. Right now we chose QPP, and the output would be what the encryption or the encrypted data would be, and what the decrypted data would be, and other parameters like accuracy, time taken, and then the report will be available in a text file.
Future work would involve overall integration of the project, including having the GUI to show and function on the monitor and be able to take input from the keyboard directly from into the board. And of course, transferring the data from the GUI in the Linux image to the DRAM, to the hardware blocks, and back to the GUI as well. This will involve more work with the Vivado software development kit to work with the created IP block and DRAM. A detailed performance analysis could be introduced to test and compare the performance of QPP to other algorithms such as AES-256. Also, simulation of different encryption attacks to test the safety of the implement QPP algorithm would be definitely something we could work on in the future. In conclusion, our group was successful in running the Quantum Permutation Pad algorithm solely on the system-on-chip board, utilizing both FPGA and processor to implement the testbed. Overall, we lacked in integrating the different components of the project, when our main obstacles being tight on time for development due to steep learning curves in terms of using new technologies the members don't have any experience for, and also delay in getting necessary programs and resources in the beginning. We still had a great time working on this project, and thank you so much for your attention of this presentation.